This week on Mega Structures Coursework Edition, TMLV Engineering face untold challenges as they attempt to build the world's largest circular skyscraper. Standing over 120 meters tall, the team will have to contend with loading effects such as shear forces, bending moments, deflection, and much more. With the building expected to withstand winds up to 130 kilometers per hour, Terry and his team's first challenge is to ensure that the structure can withstand these forces. After considering the wind pressure over the surface of the building, the team evaluate the wind load to be a total of 18.12 meganewtons over a uniformly varying distribution. For this large structure, a central concrete block provides the main support. This can be simplified to a cantilever beam to allow the team to analyze reaction forces. The evaluation shows that the greatest shear and bending moment values are applied at the base of the beam. The team decided that with such large forces at play, the structure should not have one but two central supports. But that's not all. The team must also evaluate the maximum deflection and slope caused by wind loading to ensure they have the right material for the job.
Deflection. Deflection is the degree to which an element is displaced under a load. What's the load? The load is the wind load. And how do we calculate the deflection? Well, M is equal to the Young modulus times the second moment of area times the second derivative of Y. So the Young modulus shows the material properties to see if the material is either in tension or compression. And second moment of area is the geometric property of the concrete block. And this concrete block is rectangular, so the second moment of area will be B times D cubed over 12. For the second derivative of Y, what Y is the distance from the neutral axis, so it's the deflection. And in order to get an expression for the deflection, what we have to do is we have to integrate the second derivative of Y twice. And once that happens, we can calculate the deflection at any point. For example, the deflection at the midspan would be X is equal to L2 and Y is equal to 0. And once we have this, we're able to calculate the deflection at midspan.
Now the team have agreed on the main support system for the building, they must now consider the outer skin of the building. Frames are used to support the impressive glass facade. The compression and tension forces down each beam must be calculated to ensure the structure can withstand the load of the outer skin. The team calculated a compressive force of 138.5 kilonewtons down each strut. The engineers must ensure that the frame does not buckle by making sure the load applied is less than the maximum buckling load. Material selection and cross-sectional area can increase the maximum allowable loading. The team chose steel I-section beams due to the cross-sectional area being greater at the farthest point away from its neutral axis, giving it a higher second moment than other cross-sectional shapes. Due to unforeseen circumstances, the completion of the outer skin construction has been put on hold, and the team noticed that the steel framing has begun to creep. With such a complex structure, even the slightest movement of a few millimeters could mean the remaining sections of the frame won't fit together.
So creep is the tendency for a material to slowly move or to deform permanently under mechanical stresses, even if the stresses that are under the material's maximum yield strength. This is because creep is dependent on time. It's not just dependent on time, but it's also dependent on temperature and the material's properties. And in this instance, the outer shell of Adler HQ was left incomplete for several months, and therefore it was under high mechanical stresses, and thus the framework of the structure sagged by 150 millimeters. We remedied this by hoisting the structure up into the place to complete the framework. Once complete, the structure could then distribute the load evenly through the frame and to the foundation.
The situation is resolved and the team completes the remaining sections of the steel framework to complete the skin. The final and arguably the most impressive feature of the Alder HQ building is the glass facade. The team has to make sure that the outer skin of the building can withstand the large forces that it will be subjected to, especially when using a brittle material such as glass. Fractures propagate through the material when the tensile stress at the tip of the crack exceeds the theoretical cohesive strength of the material, and can occur in three different modes: tensile, shear, and out of plane. Factors affecting fractures are temperature, skin rate, and state of stress. Cracks propagate through brittle materials quicker than ductile materials. The tip of the crack in ductile material has a plastic region that deforms and increases the tip's radius, whereas in brittle materials such as glass, there is no deformity and the tip remains sharp with a much smaller radius. This leads to a higher stress at the tip of the crack according to Griffith crack model. The team must consider all the factors when choosing the correct glass for the structure. Finally, after 24 months, the building is complete and TMLV Engineering has successfully navigated another engineering feat.